So what we do when we're trying to prepare a graph for this thing is that we select values of x, calculate what f at x equals, and then we can draw up a graph, plot our points, and draw a line. And so there's several ways that you can do that. And you know that with a line, you really only need 2 points, and then you just draw something in between it. So I could have, at minimum, perhaps just used -2 and 2, plot those 2 points, draw a line through it, and I'm good. Now, we've talked a little bit about absolute values, and absolute values, we'll calculate the same kind of table here, where we go from -3 to 3, and we see that our output values are all going to be positive. That's exactly what absolute value does. And so we're going to get this, this graph that looks like this. Okay, this nice V-shaped thing. And so for as a third example, let's take a piecewise function. And this is probably the one that we should spend a little bit more time on. How do we graph this? Now we can do it exactly the same way that we've done before. We can make up a table and select values of x and then calculate f at x. The thing that we have to be careful to do is to look at this definition here to make sure that once we're at 0 or more, that we use the second formula to calculate what these values are. So if x is less than 0, we're just going to take negative x, which in this case is 3, or -2, or 1. So it does the same kind of thing as the absolute value. But then at 0, I'm going to have this graph that, or my point is going to be 2 times 0 plus 1. And same thing with the rest of these values. So if I take a 2, I take 2 times 2 is 4 plus 1 is 5, and then the other point. So we have these points, and we then make a graph. So the first thing that we do is we take one of the segments and graph that, and then we take the other segment and we graph that. So notice what happens with where it goes from the less than to the greater than or equal to. All right, on the less than one, which is this section of the line, we go down to an open point, because if this thing was really, really close to 0 but still a little negative, we would be down here, and we can get as close to 0 as we want without getting to 0, and we'll get very close to the origin. But as soon as we get to exactly 0, we start here, and then this is the graph of the line 2x plus 1. And so you see there's two pieces of the graph that we're dealing with. That line, that 2x plus 1, deals with that part of the domain that goes from 0 to positive infinity. Okay, so one of the approaches that we can use for this is that we say, all right, when x is greater than 0, let's plot the line 2x plus 1. And we stop where this section of the domain ends. And then we plot the other one, which is the absolute value of x, or negative x is the way I defined it up there. And then for all the values that are less than x, I'm going to make the line there. So graphing piecewise functions is just like graphing each piece of the function. And in fact, you can graph the whole thing and then just erase the parts that aren't in the segment of the domain that we're dealing with. So you can have these things that look kind of wild. For every section of the domain, you can have a much different looking graph, but you just concentrate on graphing each of those pieces individually. All right, so let's look at some basic functions. And so I'm going to show a half a dozen here, and I think you've seen most of them before, but I'd like you to think of these as kind of your toolkit of functions. So when we're trying to understand functions, look at these as kind of the basic elements that we're going to form other functions from. So one of them is just a constant. If we have f at x equals 3, it's just the horizontal line is 3. Okay, so a function that is a constant is just a horizontal line. Now if we have the square root of x, we take the square root of only positive numbers, right? And so the domain is going to be restricted on this thing, and we're going to go from 0 to infinity, and it's going to go through the point 1, because the square root of 1 is 1, and it's going to increase, but it's not going to increase like a line. It's going to be a curve that increases. So think of this kind of half parabola, is what it is, thing on its side, where we're only into one quadrant. We only take square roots of positive numbers. We only get positive numbers out of it, with the exception of 0. The square root of 0 is 0. So we do have the origin and all the points in the upper right-hand quadrant. Okay, so now we have just basically, if f at x equals x, we just have the straight line y equals x. And so it's just, basically has this nice slope of 1, and goes through the origin. And then we have what's called a parabola, and we'll be dealing more with parabolas as the as the semester goes along. The domain of this thing is all real numbers, right? You can take any number and square it, but you always end up with 0 or a positive number. So you have this thing curving up. The larger the size of x is, the bigger the number you get. And in fact, it goes, the difference between x squared when you go from 0 to 1 is smaller than the difference of going from x squared from 1 to 2, right? Because the square root, or the square of 2 is 4, but the square of 1 is 1. So this thing accelerates, and that's why you have this upward curve. Or I've already plotted this, but this is the absolute value function. The slope is 1 or negative 1, depending on which side of the origin you're on. You always end up with a positive number or 0, but you can put, the domain of this thing is you can put any number that you want into this function, and you get a real number out of it. A positive, or I should say non-negative, is a good way to say positive plus 0. And then the last one is x cubed. Now, when you cube a number, you're taking the number times itself again. And so let's say if we have negative 2 times negative 2 makes a positive 4, and then times the negative 2 we get negative 8. So it looks a little bit like the parabola here, but the parabola always gives you a positive number for negative x's. The cubic function gives you negative functions when you're putting in a negative x. And so if you would just kind of remember what these basic shapes are, as we build other functions, or as you're trying to interpret what certain functions mean, a lot of them can be built with just these as the basis of it. Okay, we're dealing with functions, and of course the definition of the function is that for any value in the domain you get assigned exactly one value in the range. So how can we tell from looking at a graph whether we have a function or not? And the way we do that is we use something called the vertical line test. The vertical line test is actually fairly straightforward. Okay, let's say we have this graph here, and we want to see, is this thing a function? We don't know what the equation is necessarily, but we see that, and we see that it's some sort of relationship between x and y. And then we have another one that has another relationship that is this curve that kind of curves back on itself. The first one, if we draw a vertical line anywhere through this function, so think of this line as just any line that we can move, it only touches the graph at one point. So that means as we change the value of x of this line and move it back and forth, we're only intersecting the graph once. So that means we're just getting one value out of it. That's different. Okay, so this is a function. That's different than if we took this one. This one fails the vertical line test because it goes through the curve in two places. So that would suggest, like, I didn't put a scale on this graph, but let's say if that is 2, that we would have both a positive and a negative number as a result of 2. And so that's what that vertical line test demonstrates, is that for any value of x that you actually cross the line twice, so you have 2 corresponding y values. And that violates your definition of a function, so this is not a function. It's a perfectly good relation, okay, in the sense that we may have an equation that describes this. We may have, data that describes this or so. It's just not a function. Okay, what I'd like you to do is I would like you to graph these three functions. The absolute value of x, you've seen that a number of times, but then take a few minutes and graph x minus 2, the absolute value of that, and then graph first taking the absolute value and then adding 2. So these are going to be three different graphs. If you have different colors, you can do it all on the same graph in different colors, or perhaps you can code the lines differently, like using a dotted line or a dashed line or something like that, just to indicate their difference. But I'd like you to take a few minutes and graph this. Okay, so if we made columns with g at x and h at x, if we calculate these things right, we'll get different numbers. And so if I plot f at x equals absolute value of x, we've seen that I think twice before today. And then we look at g at x equals the absolute value of x minus 2. So it looks just like the absolute value of x, except that it's moved over to the right 2 units, that the corner of that thing has moved over. And if you do the other one, so that's moved over 2 units. And if you do the other one, the absolute value of x plus 2, you notice that it goes up. And on the negative side, it seems to coincide with the other one, that x minus 2. And that's just an artifact from its own shape, but you essentially can move graphs around by taking the one of those basic functions, one of those 6 basic functions, and if you do things to them like add numbers to them, either add or subtract to x before you calculate the function, or after you calculate the function, add or subtract to it, you can move things left and right. Okay, so this one, of course, moves up by 2 units. So what we call this is are transformations, or sometimes they're called translations, meaning they're moving around. So if we add something to the function, if we just say we're going to calculate a function and add a value to it, we're going to just move that whole function up, right? There's nothing fancy that's going to happen with the function. It's just that every value is going to be 2 or 3 or 4 more than its value before. Similarly, if we subtract something, we're going to move it down. We're going to shift downwards. Now what we did when we put the minus 2 inside of the absolute values, what we're doing is we're modifying the x value before the function operates on it. And so if we add a number to it, we're going to be moving to the left. And then if we subtract from it, like we did with that absolute value of the absolute value of 2, of x minus 2, it goes to the right c units. Okay, so if we have any given function now, let me draw a parabola in here. That was one of the earlier basic functions. If I define a function like this, where I'm going to move by subtracting 3 from x first before I calculate the function, I'm going to move it right by 3, and then with that other one, I'm going to move it up by 2, and so my new graph is going to look like this. Okay, so it actually does both. It moves up and to the right. Now, it's not just the vertex. You see, I put in the second purple line there that looks like it's crossing over the 2. Every single point in that function is mapped over right 3 up 2. So the whole thing moves. It's, sometimes the vertex or the point or some feature of the graph is the easy one to see that it moves. But any given value in there has a corresponding value that's transformed over to our new function. Now there's something else we can do, and we can make a reflection. Okay, so if I go through the same process here, I'm going to take that one that has the square root of x, and remember what that looks like. That started at the origin and it went up moderately to the right. So I'm going to make this table again, and I'm going to find that my negative numbers I can't evaluate because they're not part of the domain, right? So instead of going -3, -2, -1, I'm choosing some values that I know will give me some nice integer results to make a clean plot. So if I actually take the square root of -x, I find that the domain now is a little different. I can put any negative value I want in it, but I can't put any positive values because then it becomes negative, or the negative values become positive with a -x in there. So here I have my corresponding values of g at x that look like that. And then if I just take the negative over the function, I'm finding that my domain is the same. I can't take x, the square root of x when x is less than 0. But I can, once I calculate it, put a negative sign in front of it. So what that's going to look like then is the basic function is just going to be that curve like we saw earlier. Now g at x is going to look like this. So it's going to look exactly the same as though you put a mirror up to it on the axis, and it reflects about the y-axis. Now h at x, since I've made it negative, I'm actually going to reflect it over the horizontal axis, and so h at x, when I plot that, is going to look like this. It's going to reflect about the x-axis. So hopefully the colors have enough contrast so you can see that I'm taking this one function. Now, a lot of functions that are symmetric, of course, when you take a reflection of it or so, you might get exactly the same function back, and that's just a condition of those functions. But with this particular one, hopefully you've seen that you actually end up in a different quadrant, and in some cases your domain changes because you're making this kind of transformation with the reflections. And so if we put the negative sign inside of the function, so we take the negative x instead of just x, we're reflecting it about the y-axis, and when we put the negative sign out front before the function, it reflects about the x-axis. Okay, so I'd like you to try. First, just describe in words what that function looks like compared to x squared. What would you expect to happen with this? You know what f at x equals x squared looks like. That's that parabola. So what would you expect the function x plus 4 squared minus 5, what would that look like to you? What would that do?
To the left and down.
It's going to be to the left because you got the x plus 4. It's going to be to the left 4 units, and then down because you're subtracting. That's right. Does everybody see that? So even though this is a much more complicated function than x squared, you can still anticipate its its general shape and its location based on looking at this kind of form of the equation. Okay, so this is a different one now, and I'd like you to try this. I have this function that basically I'm going to go in between these points. So point A is -3, -2, and then I'm going to go to point B, which is the origin. Then I'm going to draw a straight line to point C, which is 1, 3, and then I'm going to go to 3 comma 4 with a straight line. And what I'd like you to do is come up with the graph of what this looks like if we take h at x plus 1 minus 3. So there's no explicit formula that I'm giving here for you. I'm giving you the graph with a few points on it. Think about how this maps over.